Right, so this is totally a work in progress talk, piece of material. So please ask questions, please give me ideas of how to take it further. So what's this about? The idea here is data types or inductive data types, especially independently typed languages, are absolutely wonderful. So here's a simple example. We've got the data type of natural numbers, and it's defined by 0 and successive. And then if we have dependent types or inductive families, we can do interesting things like talk about properties of those values by defining other inductively defined things. So here's a simple one. We can define the even numbers to be a collection or property of natural numbers, where we say that 0 is even, and we say that the successor of the number is even if its predecessor is odd. And so we have to mutually define this with this auxiliary odd data type as well, which says that if a number is odd, then its successor, sorry, if the number is even, then its successor is odd. And so this is okay, but what if we could use negation in our data types? What if we could say, instead of saying, defining this sort of extra concept of oddness, which we didn't want to talk about, what if we could say that the number is even if it's either 0, or if its predecessor is not even? So how can we make sense of a data type definition like this? What does this not here actually even mean? So this is what I'm going to try and cover in this talk after a few more examples. So here's a slightly more compelling example. So let's say we have context-free grammar. I've had a production like this. So sentence A is either an A or a B. And now for context-free grammars, we can turn these into, we can make a representation of the parse tree. So we can turn this into a data type that tries to explain what the parse trees are for that grammar. So for context-free grammar, this bar here is symmetric. So it just means take the union of the languages. What does that mean in terms of parse trees? Well, either, so what I'm representing this is parse and S is this is the string coming in, this is the string going out. So this one's always going to be a suffix of this one. And so we're saying that there's a parse of A with IO, so that means there's a parse of S, or there's a parse of B with input and output, so there'll be a parse of S. So to use this to represent, we take the ones where this final one is the empty string, then this will be all the parse trees of some piece of text. So you can think of this as a kind of trace of the parse tree. Now, context-free grammars are great, but they're kind of potentially ambiguous. So one way of dealing with this is to reason out ambiguity, use LR parsing or something like that. The currently industrially popular way of dealing with this is just to say we can't do that. Fix all the ambiguity by using parsing expression grammars. So what are these? These are ones where you'll notice here that this is now slightly off the vertical. We have the ordered choice operator. So what does this mean? This means that we try A, and if that doesn't work, we try a B. So there's this kind of built-in backtracking behavior in the grammar formalism itself. And so what this means is it's no longer symmetric. So in particular, if B is some kind of prefix of A, then we'll never get that. Suffix of A, extension of A. So we'll never get that because the A will always succeed. And how can we represent this? The parse trees or something like this using a data type as we did before. So now we need something like negation, which I'll view this sentence. So we have to say that the production one applies, and as before, we can parse as an A, for IO, and we get some representation of S. For B to be activated, not only do we need the B part, the second production to be activated, we also seem to say that any attempt to parse the input starting at I fails. So there does not exist any suffix string that parses as an A starting at this point. So in order to represent what actually happens during backtracking, not only do we need to say it worked, we also need to say that the other cases, the previous cases, did not work. So we need to represent that information. And now this gets complicated because this A, right, so I've missed out the rest of the example, but of course this A could refer to S at some point. So we have a recursion which goes through the loop, so recursion that comes back to S. So we need to define what it means to have recursive data or inductive data types that have negation in them. So here's an even simpler, more basic example. What if I define this? I say my liar type as a constructor where if only I can't prove the liar is true, then I can prove the liar is true. So how can I even give a semantics to this? Does this even should the system even allow this kind of thing? So I just want to take a step back and talk about what is usually the semantics of inductive types in a system like Atkey, how do you deal with it? So I'm going to kind of do one of those introductions where if you don't know what I mean, it's going to be quite tricky. But, usually what you do is to actually construct a kind of interpretation of these inductive types is you construct some functor. I is going to be the indexing set, so that's going to be like the natural numbers or pairs of strings or whatever. And this is something which takes like intuitively the next level down and gives you the next level up. So essentially, it's always going to be a kind of sum of products construction. So each constructor is going to be in the sum, and then each argument to each constructor will be a product. And to get the equality constraints, we assume that it's some kind of proposition equality. And then the interpretation of the data type as a whole is the initial F algebra for this F. So that gives you some I to set thing, which enjoys some nice properties, has a unique fold, you can derive induction principles from it. So this is kind of the basic theory of how to turn these inductive types into something sensible and also derive properties from it. So can we now just define not in the usual intuitionistic way and just say not A is A implies falsehood? So of course this just doesn't work. So does it work? Well, no, we're not even going to get anything that's covariant, right? So we're not going to get a functor if we try and use this. So we fail at the first hurdle. And you can try and make this work by sort of using domain theory or something like that. We're not going to do that here. What we're going to try and do is find an alternative way of saying not. So what do we mean when we say not? So one way of saying it is this leads to a contradiction. So that's what the intuitionistic logic thing is saying. Saying that if we were to sort of get A, then somehow this would lead us to a contradiction. So it sort of says that there's no way we can possibly have ever come up with this A thing. But is this what we really mean by something's not true in real life? So we've all traveled here from wherever we live, and you ask the travel agent, is there a flight at this time? And they say no, right? And they don't do that because if there was a flight at this time, it would lead to a contradiction in the whole of the international travel. What they've done is they've looked at the database said no, and they say yes. So, negation by failure of imagination. So not means I don't have any evidence to believe this. You're kind of taking absence of evidence to be evidence of absence. There is, if you've ever seen anything in this area before, you've seen this example, it's a hackneyed example. So it's a kind of intuitive meaning of not. So something flies if it's a bird and it's not a penguin, right? And if we know that bird, the Tweety is a bird, then is it safe to conclude that Tweety flies? So we're all brainwashed by logic, and we would say this is not safe. I mean, what if 10,000 years in the future, tablets are on Earth which prove that Tweety was a penguin? But ask any reasonable person, right, so this is the classically and intuitionistically, no, you can't conclude that Tweety flies. But intuitively, yeah, okay. I mean, if you're forced to make a decision, you might say Tweety could possibly fly, right? So this is the kind of thing we're going to take here, is the idea that we're going to understand not as I haven't been able to prove this. So it's kind of negation of failure in terms of logic programming. And the interesting thing about this is it's kind of non-monotonic, right? So this kind of system of rules, you could, in some systems, conclude from this that Tweety flies by understanding not as we don't have any evidence that Tweety is a penguin. But as soon as we learn that Tweety is a penguin, then we'd have to retract this belief. We would have to sort of go, no, I changed my mind. So how are we going to formally do this in the system? So we're going to have to track evidence for and evidence against membership in our inductive data types. So the way we're going to do this is by treating each inductive data type as we interpret as a pair of things. One is reasons that something is in this type, and the other one is reasons it isn't, or evidence for and evidence against. And this is sort of captured in the sort of notion that we're going to use of morphisms between these, or entailment, like where the positive information flows forwards, so from A plus to B plus, while the negative information flows backwards from B minus to A minus. Okay, so it's kind of push the positive information forwards, and we get the negative information going backwards. It's kind of bidirectional flavor. And then I'm going to call this category Q after Q spaces, because this is formally Q spaces on the category of sets with one, the number of objects is the kind of A. And also want to say that you can also take the bottom of the empty set as the constant here, and that means that somehow the true and false can't be both true at the same time. So we get a kind of para-consistent thing if we do a like this. We could also add this, but I'll skip this for this talk. And then this has a really nice sort of set of connectives, a nice intuitive meaning. So we define conjunction of two of these things by, let's think about it in terms of evidence. So if we want evidence for both of them, then we have to have evidence for both the positive parts. But to refute it, you only need to refute one half, right? So we need to refute the either refutation for the first one or refutation for the second one. And the sort of dual applies for disjunction. So we either need to prove the first one or prove the second one. But to refute it, we need to refute both of them. So we need to supply a pair. And these extend to infinitary things. So just on the conjunction here. So if we've got a set X and a family of these positive negative pairs, so we take the universal, the pi in the positive part, and to say this must hold for every single X. So every X you give me, you must give me a piece of positive evidence. But to refute it, I only need to give you one piece of 1X and to refute that. And we put the sigma here, then we get the dual, we swap the pi and the sigma.
But X is an honest set here.
X is an honest set. And negation, this is the nice part, we just flip the positive and negative information. This is what we're going to use to interpret negation. And then also we can incorporate every set by taking the positive information is the set itself, and the negative information is the representations of that set. So now, we're sort of getting there. So we can interpret these data types I put up last time. But let's for a moment assume we don't have not, because it's going to be easier. So if we only do it from the positive connective, so times plus pi sigma in sets, then it's quite easy to see that if we define f in this way, we can actually separate it because kind of the positive and negative things never cross. Because we don't use not, then we can separate it into the positive and negative parts. So an f plus and f minus, and these are both just on sets. Right, so all the positive information only goes to the positive part, and the negative information only goes to the negative part. And then we can construct initial algebras in Q, just constructed from those in set, where remembering that the morphisms in the negative part go backwards, we use the greatest fixed point for negative information and the least fixed point for the positive information. So the least, or the initial algebras in Q are initial algebras in set for positive information, the final algebras for the negative information. Because sometimes we might have to give intuitively infinitary refutations to some facts. Like there's all these different ways of it might be true. We have to sort of bar each one of these, whereas we might only have to give a kind of finitely amount of evidence to say something is true. So let's see how it works. So remember, we can't do negation yet because that will cross the streams, so to speak. So let's see, here we have this kind of path data type, which is a kind of reflexive transitive closure of this step one that the students just given. So either we stop and we have a path which goes from itself to itself, or we have a path from x to y, there's a step from y to z, and then we get a path from x to z. We translate that into a functor. So this is a functor on Q. So parameterized by the x and z, either x equals z, the translation of this kind of repeated variable in here, or there exists a y, it's a step from x to path from x to y, and then a step, receiving steps are just some set-based thing. And now if you separate the positive and negative parts, you can see how this is going to work. So in the positive case, we get the usual so a translation of the reflexive transitive closure of a proposition or a relation. And here, well, what does it mean to refute the fact that we can like reachability? Either they're not the and they are not the same thing, so we're not already trying to link up to the same place. And also, any attempt to find a kind of bridging spot will either fail because there's no way of linking the two, so kind of referring to the x minus, or we can just say that there's no way of getting from that bridging spot in one step to our final destination. So when we take the greatest, the final algebra of this functor, this is going to be refutations to the fact that x and z are linked in some relation. So this is quite nice already. We've got a kind of automatic way of talking about kind of negation of a data type by saying, by sort of having a constructive refutation of it. But what about data types? So this does bring back to the topic of presentation. And what about actual data types and negation? So we can't do those yet. So what I'm going to do is define another category with the same object as this two one, but it's kind of 2i for information. And in this category, the morphisms go both in the same direction. So we go from a plus b plus and a minus b minus. And so one way of thinking about this is this kind of an information ordering. If you think of these kind of ordering, we're kind of processing information, going higher and up, adding more, so processing more and more. Do more and more processing as we go. And if you replace these with Booleans, for instance, then you can kind of see this is sort of moving up the lattice of having more and more information. And one important thing is that now negation is now covariant in this category, unlike before where it was contravariant. And again, we can construct initial F algebras in Q-eco. And these are now just kind of like mutually defined things, because we just take the fixed points and both of them together. We can actually cross things. They're just mutual definitions. So it seems like it might work, right? So now my thing would be to do, well, we just take the f from the data type and apply this fixed point, and we'll get something. But this doesn't quite work, but it gives the wrong answers, right? Because we don't actually get a proper refutation in the last component. So we're going to have to somehow combine these two ideas. So the way to combine them is some ideas taken from logic programming and non-monotonic logic programming. So what we're going to do is we're going to take the positive meaning of a data type and then refine it by some information we already know about things that we can't derive. So this is called the reduct of a logic program from stable model semantics. So given some functor that's been derived from a data type of negation, and some information we have about things which are not derivable. So this is things, both things which are derivable and not derivable, because we're going to need both to handle negations. Then we can define this f over y thing. So for any x, there's a x plus and x minus. What we're going to do is, in the positive half, use the positive information from x plus. We use the negative information from our kind of pre-stored graph here from y. This is sort of, so if you think of y as the kind of our previous state of knowledge about what we could derive, this is saying all the negative stuff is taken from y, but we're just deriving new positive stuff. And on the other side, it's the other way around. We're using the positive stuff from y and we're deriving new negative stuff. So y represents a kind of stage of knowledge that we're building up.
10 minutes left, including questions.
So y represents, okay, I'll stage mode. And this now thing is kind of separable. This thing is now separable, right? We can separate it into this half here only depends on the positive part here, and this part here only depends on the negative part. So we've got, for every y, we've got a functor, a separable functor from q to the I to q to the I. And so this means that using the construction from before, we can take the initial algebra. So we get mu of f over y is now a legitimate object of index 2 sets. And moreover, this is factorial in the y's. So now we get an information functor, a functor on the q information. That is, take the initial algebra in q with these truth morphisms for any particular y. And then this allows us to kind of give an overall semantics to these data types with negation, which is to, given the f, we take the information fixed point, these style fixed points, over the truth fixed point with respect to these stages of information. And then if you spell all this out, you get this kind of mutually defined positive and negative information, where each stage of the positive information is done taking initial algebra, and each stage of negative information is a final parameter. So this is sort of a bit mysterious, and part of the reason that this is just a talk abstract and a full paper is this is kind of what's in. So I don't know how to reason with these in a useful way, but let's see some examples. So first, so a kind of useful fact is that if you replace set by bool in these things and add the q bottom constraint, so we make sure that it's not basically not the case they're never both true. And then this coincides with a sort of previously studied 3-valued stable model semantics of logic programs with negation from the 90s. So let's work through some examples. So the liar example, perhaps the simplest one. So as a functor, this is just going to be f of x equals not x, interpreted in these two connectives. So we can separate that out to f of x, well, f plus of x equals x minus, and f minus of x equals x plus. And then once we compute through, it's going to be isomorphic to just bottom in both parts. So if this was a 3-valued semantics, this liar paradox would be given the indeterminate truth value. We can neither prove it, nor can we refute it, I think. Just to show it sort of works, let's take the no base case functor, so data type. If we do this one, then, well, that's the underlying functor. And in this case, we'll get, because we get mu x x and mu x x, we'll end up essentially with, there's no proofs of this because there's no base case, and there's one refutation, which is kind of the infinite list of units. So yeah, no proofs and one extension with one refutation. And my final example, so if we take this representation of even, where we had 0 is even and a successor is even if its predecessor is not even. So now the functor looks like this, where I kind of use this pattern matching to do the cases. So f of x, if it's 0, then this is terminal object in Q, which is true, of course. And then the successor is not the x factor, yes. Separate these out. So now this means that in the positive case, 0 is the terminal object. In the negative case, 0 is the initial object. And in the successor cases, we flip the positive and negative. Now you might be able to see where we're going here. So once you work it all out, we actually end up with the same as it was before in that kind of mutually inductive definition, right? So we've got y plus, which we can think of as even, y minus, which we can think of as the odd, and then something's even in the positive case if it's 0, or its predecessor is odd, so y minus is odd, and it's odd never when it's 0, and if its predecessor was even. So compiling this out, if you like, actually gives you back two mutually defined even and odd. So there we go. So I think what I managed to do is construct a reasonably plausible definition of what it means to be a data type with negation. I think it's plausible looking, and in some sense, I've just stolen some work from 30 years ago from the logic programming community and written a set where they were all nearly. That's not quite true. They really love their syntax there. And I think, even though I haven't written it out as one of my examples, is it's potentially useful for modeling backtracking processes. So it's kind of difficult to think of really compelling examples, even and odd. It's not that great, but I think backtracking processes, like what is the parse tree of a peg grammar, it really does start to shine there, because otherwise, if you want to include negation, then you're often forced to stratify your definitions, but within a grammar, there's no easy way to stratify it, because the only way to stratify it is by distance through the input. Mention some related work. So recently, this isn't the only work in this direction, but recently there's a paper by Mike Schulman on the antithesis translation, where he uses this true construction positive negative information to sort of rephrase some definitions in constructive mathematics, and get sort of quite a lot of mileage out of there's all of these sort of itty-bitty things that constructive mathematicians have been doing can be summed up just by choosing the right kind of negation and disjunction means. I mentioned already weak negation, negation as failures. This is ideas that come back from logic programming. And also kind of hidden in this is some ideas from bilattices. This is structures where you have the same set, but there's two interlocking lattice structures on it. So, you know, to do implementation Agda on the way, and possibly after that, reasoning principles. So you've got to derive a reasoning principle from the fact it's a nested fixed point, but that's surely too difficult to use. Thank you for listening.